All right. So just I put a few slides together here to kind of walk you through a little bit of our approach. I kind of want to start a little bit with our soil carbon pedigree. I think we're known, like John and Neil, you guys know us as the soil conductivity sensor people and maybe a little bit beyond that. But we've really actually been working in soil carbon for 20 years now. Back in 20 years ago, we got a USDA grant to develop, vis-NIR spectroscopy, visible near infrared, to do on-the-go sea measurements. And in 2002, we were up at the USDA Soil Tilth Lab working with David Laird.
David Laird.
Yeah. And so this is our prototype machine. And there on the hillside behind my colleague Colin Christie on his little prototype vis-NIR sensor, a couple guys taking soil samples. And they took 160 plus soil samples on 40 acres. And that's the map on the left. There is the map of carbon from the lab samples. And there on the map of the right, back in 2002, is our near-infrared spectroscopy measuring soil carbon. You can see, the map is very similar. So that product morphed into a commercialized vis-NIR spectroscopy system that we sold kind of around the world to carbon researchers and spectroscopists and just soil scientists who are interested in that kind of highest level of vis-NIR type measurements. In 2006, the Department of Energy granted us some money to develop that same technology into a probe for measuring profile carbon measurements. And that's what that probe looked like and some examples of what that could do. And so, as Tyler mentioned, and I said back in that mid 2000s, we were really heavy into this carbon. We had these government grants. We were doing carbon projects for EDF and a number of different entities. We published papers. In fact, here's a poster on the right with Chuck Rice. There you mentioned. We actually co-author. I'm kind of proud to have had as a co-author one of my papers, a Nobel Prize winner, because I think Chuck was part of that Nobel Prize group. So we were really heavy into different ways of measuring carbon with that technology, because it looked like at that point, boy, soil carbon is going to be part of the greenhouse gas or climate change reduction approach. In 2010, we introduced an on-the-go organic matter carbon dual wavelength system. So rather than the spectroscopy system, which requires almost a chemometrician who's familiar with working with 300 wavelengths. We mined our data set and found a one in the visible, one in the near infrared that were really rich, and we developed more of an LED type approach, and that's really what we market today. So these are all examples of our on-the-go, real-time, dual wavelength, more simple, commercial, affordable systems. They mount on, they're embedded on planters and tillage tools, and we have it on the probe, as you can see there on the front of the tractor. And so that's kind of our pedigree from kind of the really high-end spectroscopy now to units that have fewer wavelengths, but really produce really comparable results.
So Eric, what depth these measurements were taken?
So the typical measurement approach with the on-the-go system is just like 4 or 5 centimeters. So we're just mapping the kind of the XY distribution in a field for precision agriculture primarily. The unit there mounted on the probe of the tractor is the unit that we map down to a depth of 3 feet. So we're able to actually get some carbon measurements done. And I'll go into more detail on that. Actually, kind of the rest of the presentation really focuses is on how we use the probe measurement more than the surface measurement, okay?
Right.
And so now we have these units. Our equipment's in use in over 30, total our equipment's over 50 countries, but these vis-NIR systems are in use of over 30 countries on 5 continents. So if we think about agriculture missing the opportunity to contribute to greenhouse gas reduction and to profit from it, one of the challenges is the increase in carbon over 10 years is small. I mean, if we think about it in terms of kind of percent carbon in a 6-inch sample, it's from maybe 2 to 2.5% carbon. But if we think about actually in agriculture, there's more carbon variability in a field within short distances than that expected change. So actually, here's that data from that Iowa State, near Iowa, near Boone, near Ames, where those samples, there were 160 samples on 40 acres. So you can see in these 2.5 acre grids, the range of carbon within each of those 2.5 acres is way more than the expected change. So if you move just a few feet away from one sample, you've either increased carbon by 2% or decreased carbon by 2%, you know, which is just, I mean, nobody's going to pay real money for carbon if they can't be sure that you're in the right spot in the field.
I have long-term studies in that area. Go ahead, I'll mention it to you later.
So that's one of the challenges.
Yeah.
So what that adds up to, and this is just a very simple graphic that shows, you know, you go out at year 1 and you get a carbon measurement. You come back at year 10, you've got a difference. But what is the real difference? If we attach the error bars, the uncertainty bars around that, it's very, very possible that we really can't detect any measurable carbon. This is what I think environmental defense and others call the reliable mean estimate, where you look at the upper, you know, the upper limit in the beginning and the lower limit at the end, and that's basically the margin of error. So let's look at how soil sampling and soil sensing can help this. So this is actually just this first field I'm going to show is kind of a theoretical example to keep things simple. This is a presentation we've been doing to farmer groups. So we've really kind of tried to make, you know, the confidence interval, you know, people's eyes glaze over. You know, I realize on this call, you guys are all used to these terms, but most farmers, it's like you really have to kind of get their attention. So let's look at this field. So to calculate the confidence interval, we need the standard deviation, the mean average, and the number of samples. If more samples reduces the confidence interval, et cetera. So let's say we go out there on this field and we take 5 deep cores. And that's not a cheap measurement to take 5 deep cores on this 100-acre field. So that the confidence interval is typical of confidence interval. What we found on this field would be 4.38 tons. So there's 36 tons of carbon and those 5 samples. So year 1, we start out at 36 tons per acre. 10 years later, we've added our 1 ton per acre. This is in acres, so you know, bear with me. We don't do the megagrams of carbon per hectare when we're talking to farmers. So you get that 1 ton per acre. So if you think about $40 a ton, farmers could get $40,000 if they could account for all the carbon. But you apply the confidence interval to this number. Now all of a sudden, you only collect money on 1.2 tons per acre. And so rather than $40,000, you're at $4,800 minus the cost of the sampling. So you're at $4,300 net profit. So even with 5 samples per acre, it really, the confidence interval, the uncertainty really comes into play. Let's move up and let's take 100 of those 30-foot or those 3-foot cores. It's going to cost more to sample, but let's see if we can get there by just sampling the soil conventionally. So yes, we do shrink that confidence interval in this case down to 1 ton per acre. So we start out at year 1, come back at year 10, 46 tons, confidence interval of 1. Now we're getting a lot more carbon. We're getting 8 tons out of that 10 ton possible. So that's a lot better. I mean, we're at Veris, we are pro measuring carbon. Whether you measure it with soil samples, whether you measure it with sensors, we believe measured carbon is better than unmeasured carbon. So rather than the 40,000, after we take the sampling cost, we're at 22,000 net profit. So it's better. More samples is better. But here's where sensors come into play. So let's say rather than using all samples, we start using sensors on here. So we first characterize the XY variability of the carbon rapidly with our on-the-go system. And then we can use either embedded sensors on tillage tools or a cart-based type unit. And we get a map of the carbon distribution of the surface. So with that, we come in there and we take a handful of deep carbon measurements with our probe. And those are represented by the red dots. And the green dots then are sensor probe measurements, where we take a sensor probe and extend the measurements from those lab samples. So here's the way that works. So here's our carbon probe. We have a force sensor, we have an optical sensor, and we have a conductivity sensor to get the soil texture. And as that probe goes in the soil, we're actually developing with the calibrated lab samples adjacent to it an actual soil carbon measurement from sensing. And here's a little video. We did a project, actually, John, this was a company you used to work for. And so we took a bunch of soil carbon measurement or soil measurements. And here's taking a core sample. This is Tyler, by the way. So you can see taking a lot of you have been out in the field, so you know what it's like to take a 3-foot core. So it's not like a little 4-wheeler taking a bunch of little samples. It takes some equipment. So there's the 3-foot core that will go to the lab for analysis. And now here is the sensor probe taking an adjacent sensor reading that'll be used to calibrate that then. Well, let's see if I can move on.
Were you guys taking bulk density measurements with that probe?
Yeah, let's see if I can look. Yes, so we measured on those lab samples, we measured bulk density and soil carbon. So we were, even though our sensors weren't, oh, shoot. Hey, Tyler, how do I move on from this slide? There we go. Yes. So what that means then is we reduced the confidence interval down to 0.4 tons because we took a sensor reading at every one of those, every inch of insertion. So we're using soil sensor measurements to increase the number of samples. Mm-hmm. And so that's how we get the 95% confidence interval at 0.4. So now we apply that to this metric and we get 9.2 tons. And so that way we increase the profit to the farmer to 33,800. So obviously there's a sensing cost and a sampling cost, but we want to reduce that. But the important thing too is when you're all said and done, you don't just have some sensor readings for the purpose of carbon. You have a precise soil map, probably the world's best soil map you can ever have, because you've got, a Veris map of the surface carbon and then some type of understanding of the soil profile. So in terms of NOx reductions with better nitrogen applications, you can look beyond just the carbon sequestration side and move to a lot of applications in precision agriculture that can be advantageous. So if you put this in terms of a farmer on a 2,500 acre farm, right now these programs like Indigo and Farmers Business Network and some of these, it's kind of a one-time $10 payment. You have to share your data. You're not really even sure what who's buying the carbon. So a 2,500 acre farm gets $25,000. Okay, $25,000. But if you take the 5 soil sample example, even with all that uncertainty, you jump that to $107,000 over 10 years on 2,500 acres. And if you go crazy with 100 soil samples on 100 acres with all that cost, it's over $500,000. And if you go for the best deal with precise soil sensor maps, sensor probing, calibration samples, $845,000. So this is why sampling matters and why sensing and sampling is an even better approach. But before we kind of open this up to discussion, I want to show you a real, this is kind of fictional example to keep things simple. But about 10 years ago, we did a soil carbon research project that measured carbon changes on long-term tillage trials across 5 states. Environmental Defense came to us after we'd done another project for them and said, hey, we've got money. What would you like to research in carbon? And at this point, Ratan Lal from Ohio State, who'd been a real advocate for soil carbon, had just published a paper where he found that there was more carbon in the top 12 inches, but less carbon in the deeper, that it was more of a transference of carbon. And in his study, he really kind of went against everything he found earlier and said, I'm not sure soil carbon could really be sequestered when you consider the whole profile. So we went to the Environmental Defense and we said, we want to find some long-term trials where there's been side-by-side paired, conventional farming, no-till, manure, cover crops, whatever. So most of these were USDA sites. The one in Pennsylvania was a Rodale site where they were really intensive on carbon. So here's an example, and I want to focus in on Nebraska. So John, you'll recognize probably some of this. So Nebraska had a long-term tillage study going on, and it compared corn, soybean, conventional tillage. So basically business as usual, no conservation effort. And there's some red boxes around those strip trials. They also had corn, soybean, no-till. So just that next level up of conservation. And there's those yellow boxes. And then they had no-till corn. And I don't think there's very much no-till corn on corn. So I guess I'm proposing that this would be similar to like a corn, soybean, no-till with cover crop. So it's a very aggressive, no manure at this point, but just pretty aggressive carbon sequestration. So we went there with our probing technology, and we probed each one of those sites. So here's the conventional tillage, where each one of those red dots is where we took a sensor measurement. And then we did the same thing on the other trials. And the brown circles you can see behind there is where we took calibration probe samples. So even though this is, a very few acres, this was as intensively sampled as like this 100-acre field, maybe even a little more intensively sampled. But it was kind of our ability to get into a time machine and go from conventional tillage over to, well, what would happen if we no-tilled for 10 years? Get in the time machine. Well, what would happen if we did, a really aggressive precision, conservation practice like cover crops or continuous corn, a really residue intensive approach. So what we found is that when you move from a conventional corn soybean to no-till, just no-till corn soybean, you increase tons of carbon per acre, almost 4 tons over 10 years. And so that would be $150 payment if you were at the $40 payment level, $40 per ton. So for a 2,500 acre farm, $375,000. But we moved to the really aggressive corn on corn approach. There we got the 1 ton per acre, per year. So over 10 tons in 10 years of carbon per acre. And this, what's exciting about this for us was not only did we able to kind of show what sensors can do, but we were really testing this whole idea of, can soil sequester carbon? And can it be measured? And so this was exciting to us that we found over 10 tons of difference in that. And so there's your $1 million on a 2,500 acre farm. And of course, if we apply the confidence interval and we use the samples only, we have 40 samples. We have over 2,000 sensor samples. And so the way that works for the confidence interval, is, the more more samples you get, the more carbon you can capture or you can account for. And so the difference between $640,000 and $937,000. So that's kind of our approach to measuring, to spending the money to capture the XY variability, but then taking these profile carbon measurements to really prove that you didn't just change the top 2 or 3 inches of carbon, you changed it within the whole profile.
Right. Eric, those plots, are those Polyasas or the USDA plots? Or can you share that?
You're asking a 65-year-old guy to go back in his memory over 10 years.
Yeah.
They
They look like they're out east of Lincoln. Those.
Yeah, they were. We actually worked with Newell Kitchen, they're in Missouri, to kind of help line these up. So I think they're USDA.
Yeah, I've pulled a lot of soil samples from those plots, I think.
Yeah, they are, John, ARS, because there's several ARS station, Ohio and Iowa and Nebraska and many other states. They have these ALTAR, they call them.
Yeah.
Long-term ecological research station, which is developed. Actually, I have plots longer than these, and I was surprised, Eric, you didn't contact Iowa State for that. I have plots for 20 years in 3 crop rotation and 5 different tillage systems covering the whole state.
It'd be great to do a project like that. We actually wanted to do more than we did, and we just kind of ran out of time, and the project needed it. But we found, I think, what we wanted to find, and that's that soil does sequester carbon when you look at the whole profile using the right management practice. Not every practice, not every conservation practice that the COMET model might say, oh, this is going to sequester carbon. Not every one of those did it, but there was carbon sequestered.
What's your plan to do it out west, where it's a dry land system, semi-arid?
Right.
Those are great samples, and we have LTRs out here as well. But I'm more curious on semi-arid systems with granite and salt soils.
Right. Yeah.
Not so much the Midwest per se.
Yeah, because when you go in the Midwest, you deal with mollisol, and the carbon change in the mollisol is ridiculously low.
Right.
Because of the soil foundation, prairie system, rich organic matter, and also the high temperature, the low temperature and high moisture. The carbon,
high temperatures, low moisture with antisols.
Right. It's a great contrast in the West. When you have arid climate, you have different soil formation.
Even though we have the ability to sequester carbon as well.
Right.
What is the interference with the parent material with these probes? Because mostly mollisols are well-developed soils. So those are kind of my initial questions. And then how do you map that bulk density from your information, not just the carbon, because that could be a correlator in the map to capture spatial variability as you cross the landscape.
Right. Because when you look at the soil mineralogy, is going to be a huge factor in carbon sequestration. And that's plus the climate, which is temperature and moisture. And the last paper I released, 15 years long-term tillage studies and 7 locations across Iowa. It's published in the Soil Science Journal of America, if you want to look at it. Eric. And the average carbon, when we look at the 3 crop rotation, there is little effect for the crop rotation on the carbon capture. Mostly the intensity of the tillage has a lot to do with the carbon sequestration. We lost carbon with all conventional tillage, which is deep rip, chisel plow, and Marlboro plow.
Mm-hmm.
And we gained carbon with strip tillage and no-till over 15 years, approximately 0.3 to 0.35 megagram per hectare.
Did
Which
you
is,
show any difference in different ag crops like corn versus alfalfa, which stays in for 7 years and has a deeper root system, so it could take it down farther?
we didn't do other crop rotation. The only 3 crop rotation in our study is corn, soybean, corn, soybean, and continuous corn. So these are the rotation we examine, which is dominant in Iowa. You have a 27 million acres split between corn and soybean. So we found that kind of support your statement, Eric. It's the carbon sequestration ridiculously low because of the soil variability. And the example you give in the Boone site, because you have a different soil types in the same field. And you have Consteo, Webster, for example, and that's dominated, and Clarion dominating in Boone. So when you sample across these, not by soil type, your carbon chain absolutely non-exist because of the change in the soil type and mineralogy.
Mm-hmm. Mm-hmm. Well, I think those are all great comments and questions, and this, but by no means did the work we did 10 years ago answer all the questions. It just kind of answered, I guess, the questions of time. I think certainly different soils are going to sequester carbon at different rates, and I think that's one of the reasons why there's uncertainty is there's areas of the field that probably won't sequester any, and there's probably areas that'll sequester 2x time. So it'd be pretty easy to kind of game the system a little, or have the system game you, I guess, if you didn't do it right. Let me just kind of finish this, and then we can open it back up, and I'll stop sharing. But I wanted to just I think just takeaways that we kind of like to share is that it does require effort to do carbon. And I've just been traveling across the Corn Belt the last month doing another project, and you don't see very many cover crops. It's cover crops. There's an expense. The no-till farming I've been no-tilling on my own farm for 25 years, and there's times where you really would like to go till because you've got ruts or kind of other issues. So there needs to be probably some incentive to add carbon. I think the question that has been plaguing agriculture is that, well, maybe agriculture adds carbon, but you can't measure it. You can't measure it. No, you can measure it accurately and affordably. I mean, we're talking $30 an acre to map carbon the way we propose mapping it. And that is, when you look at the potential income from that, percentage wise is an affordable amount. If we get to a real market rather than this free for all we have now, where nobody really wants to spend any more for carbon than they have to satisfy their stockholders, agriculture really should be part of it. I think the current programs grossly undervalue potential carbon revenue, and I think this, going back to that mid 2000s when we saw ag being left at the side. If the more agriculture gets the reputation that it can't measure it, and you just have to give the farmer a little bit of money and use models only, no validation, it's really going to undermine agriculture's true potential. And it just won't have the role it could have and really should have. So just where we're going, just my final slide here. So Veris, we continue to advance the cause of measured soil carbon programs, just continue to work with different entities like yourselves to understand this better and to wave the flag for, don't take $10 when you could get $40 every year kind of a thing. We really recognize that this whole soil carbon measurement, I mean, a lot of our measurements for soil carbon were really done the last round of excitement, 10 years ago. And we need, like you described, more arid environments, more just different approaches. So we have a capacitance sensor that measures soil moisture. And we've it's been commercialized for a couple of years. It is not currently part of our soil probe. And so we have this new DOE grant that, John, that I think you referenced, that Soil Health Institutes got as well, working on some soil measurements. We have a grant that we've been approved for adding that sensor to the probe. And so that's really going to help us develop a bulk density approach. Because if you think about bulk density and the need for some kind of pedotransfer function, if you have an optical sensor that's measuring organic matter, you have an insertion force sensor that's measuring kind of the compactness of the soil, moisture sensor, and a conductivity sensor that's measuring texture, you've really got the four main factors that affect bulk density.
Right.
So part of this project is to make this probe more deployable with mounting in a UTV, and really understand this bulk density even better than what we've done, and automate things so that we can go out and measure, kind of a carbon probe type of an approach.
Right.
So that's what we're working on.
One thing I should add there, Eric, when you talked about carbon, one of the things that you should be thinking about as you're doing some evaluating soil properties is the additional carbon organic matter in the soil is going to increase water holding capacity of the soil. So that's another value added calculation you might want to consider doing. Because
I think that's the frustrating thing. Back in I don't know if this is still being talked about, but some of the other ways of carbon capture, are like pumping CO2 down abandoned mines, putting it in barrels and dumping it in the ocean, where there's no secondary benefit at all. And agriculture, the secondary benefits of soil health and NOx gas reductions and all the things that more carbon and a better soil map can do. Right. It's just a crime for agriculture to be kicked to the curb as they really can't do it right. Yeah. So we're not, we're going to put CO2 in barrels instead of in the soil.
These 100 farmers we talked to, they indicate, I think they'd like to get some of the legacy value for what they've been doing for 20 or 30 years, but the additional benefits they're seeing from increased resiliency underwater, drought stress and things like that, they basically said we're making money without them. But people early on, when they adopted these practices, it cost them sometimes. They made some mistakes, and so getting some upfront cash to help you offset some of those upfront costs. This is where the carbon market could come into play. And 10 years down the road, who knows whether they need to continue getting that money or not? But it gets them in the game. It starts to get them to start accrue those benefits that come from increased soil organic matter.
That's right. That's right.
You've been thinking organic matter all your life.